Okay, we're back for installment 2. So we have found a total resistance for this circuit of 965 ohms, and this was helpful to find that series equivalent resistor of these two parallel resistors. But now we look back inside here for a bit. So I1, we're looking for the currents here. Well, I1 is the current through, well, firstly you've got to identify what component or components I1 is going through, and in our case there's two things. There is the battery and there is that resistor there. I1 does not go through R2 or R3, it splits, and some of it goes through I2 and the remainder goes through I3 of I1. So, but we can focus on these things. Now, probably the easiest way to look at this is to think of it from, again, that battery perspective and say, okay, or the whole circuit perspective. I1 now, using our Ohm's law formula, okay, V, this is going to be important, draw your triangle up in the top corner when you do this, but I is equal to, let's just work our way through it, V over R. Okay, now let's have a think about this. V, for the whole circuit, we have V is 9 volts. So this whole network of resistors sees 9 volts across it, and its resistance, of course, is 965. Therefore, if we do that, I've already got that value still on my calculator. 9 divided by the answer is equal to, and now this is one of these things where I would actually, if you've got an answer with exponential answer, I'd probably get it down to its rawest form, because it can get a little simple. That's in milliamps there, but you want to get it down to amps, and we'll just have to work out how to do that. I'll just see if I can. There you go. If it has zeros there, that is the raw answer. So we actually have an answer now of 0.00933 when we round amps. I think it's probably easiest to keep it that way, which of course equals, what did I say, 9.33 milliamps. But use amps when you do calculations. You've got to get it into amps form. Okay, right, now the next part, this is where it can get a little tricky. I2, how much current is going here versus how much current is going there. Now let me just say, if you have got two identical resistors here, like a 1K and a 1K, well, how much of the current will go this way versus how much will go that way? What do you think? You know, any thoughts, Dylan?
Half, half.
Yeah, half, of course, because this will split equally, because you've got the same amount of resistance here, same amount of resistance here. So let's 9.33, you divide that by 2, and it would go either way. And you could actually say I2 equals I1 divided by 2. And in fact, there will be some questions you'll be faced with where it actually will be that simple. But we're going to go a bit more tricky here and show you what you need to do from here. So in fact, if they were the same, easy, you could actually halve it and then make it the same. They'll be the same and you can carry on. However, it's a bit trickier here. So in fact, this is the wee problem we have is the order of questions here are not the order in which you would solve it when you've got a tricky problem with two different resistors. You would solve it in this order: 1, 2, optional, and then you'd go down here 3, 4, 5, and then you'd do 6 and 7 there. Okay, so often with these things you don't necessarily solve in the order they ask. You just chip away at it and get things as you can. So let's have a look now at VR1. Let's see if we can do this. So V, voltage, according to our formula over here, is equal to I times R. Now, have we got enough information for that here, for R1? I, have we got the I through R1? Yes, we do, because of course I1 goes through R1, so we've already got that, we've calculated it here. And then the resistance, well, we've got that as well, so we can do that. So we can go equals 0.09, whoops, another 0, that could really stuff things up, couldn't it, times 560, which equals, and if that's the value there, isn't it? Yep, okay, so I can still keep going, I don't need to add anything else, I've got lots of detail there now. 560, which equals 5.22 unit, it's volts, isn't it? Okay, Right, moving on. Now, can we do an I times R here? I times R. Okay, so we know what R this now I2 VR2, the voltage across R2 here. Okay, we don't know I. Hang on, we need to do the I here. But hang on, we need to do the V here to know the I here. But we need to do the I here to do the V here. We've got a chicken. Oh dear. We're going to take a pause. We'll be back. Right, apologies for that rude interruption. That was what I have nicknamed the death metal bell. And as that was going, what I was about to say is we've got a chicken or the egg problem here. Which goes first? We want to find I2, which is the current up here, and then we also want to find the voltage across it here, VR2. The problem is, in order to solve I2 using Ohm's law, we need VR2. But in order to solve VR2, we need I2. So we can't actually just use Ohm's law straight there. So we've got to resort to some other tricks. And there are a few of them, but I'm going to, as you see, I've numbered this. I'm going to tackle this one here before going the voltage before going back to the current. Just because I think that's probably the best approach to take. So we have to consider, and I've already started writing here, we have to consider the voltages around the circuit. So in fact I've already drawn, look, we have a volt. If we go around we'll make it, just choose one path to get from the positive back to the negative again. We're going to go around, we'll take the inner path around here. Okay, so we're going through the battery, which is a rise. Battery is 9 volts. Now, the sum of the voltage drops around a circuit should equal the voltage rise, or sum of voltage rises. Okay, so we've gone through this 9 volts, and on the other side we have got, firstly, we have got this voltage here, a voltage drop. Now we know that, we've calculated it, and it is down here. That's VR1. In fact, I've made such a mess of this thing, I'll do it again. So we're going to go 9 volts here, 9 equals, that's the rise there, 9 equals, now this is 5.22 plus any other voltage drops. It must be, because of course this has to equal 9, and that voltage drop is, oh look, it's here, it's I3 actually, it's VR3, so I probably should have gone around the outside, shouldn't I? Suffice to say, it actually doesn't really matter, which you'll see in a minute, because if we VR3, okay, 9 equals 5.22 plus VR3. So in other words, we need to rearrange this to say VR3 equals 9 minus 5.22. Okay, sorry, it's getting a bit messy now, but 9, yes, deal with it, minus 5.22 equals, so it's the difference there, which equals 3.78. In fact, we can write it all nice and neatly again, of course, can't we? VR3, that is, so we've jumped down to this one, apologies, equals 9 minus 5.22, which we can use this equals here, which equals, and I've already calculated that, 3.78. Now, by the way, I could have gone around this, I could have taken an outside path. I'll go red again, take this outside path, 9 minus 5.22 there, minus this voltage, and that was the VR2 that I should have gone for had I not made a mistake. And so it's actually going to be the same thing here. So it's going to be the same thing here, 9 minus 522. Or, I mean, that's one way you can do it, 9 minus 5.22 equals the same thing. Or, I just put an or here. Here's another way of putting it. These two resistors, they are in parallel. Now, what do we know about any two components in parallel? Well, they are in series. We learned it in the parallel circuit with just the 9-volt battery down here. So, in fact, another way of saying it, if they are in parallel, they have the same voltage. We've already calculated VR3 here, so that means VR2, in fact, does equal VR3. Or vice versa. I should have done VR2 first and then solved for VR3, but I didn't, and I've spent too much time on this already. So therefore, basically the answer is, irrespective of how you do it, the answer here is going to be the same. Okay, 3.78 volts. They are both the same. Okay, different resistors, same voltage. Okay, and okay, different resistors. So how come the same different resistors produce the same thing? Well, they produce the same voltage. However, what's going to be different about them? It's going to be what current goes through them, and we should now be able to solve that quite easily. So I2, what we always have to focus on a resistor if we can. So I2 is the current that goes through the 1K resistor. So we're going to now go, okay, I2 equals I is equal to, according to Ohm's law, I equals V over R. So I, as it says just there, let's get back to black again. I equals V divided by R. Now let's focus on this resistor, which equals now voltage across that resistor. We've calculated that, and that is down here. That is 3.78. 3.78, whoops, divided by, haven't left much room for a denominator here, have I? Divided by, I could do a divided by sign, of course, divided by the resistance, which is 1,000. Now, ohms. Now, should I don't need the calculator for that. We should be able to equal 0.00378 amps. Okay, that yep, that makes that goes without saying, or which also happens to equal 3.78 milliamps. See, divided by 1,000 takes you to milliamps. Okay. Now, and then I3, again, nice and easy, equals V over, it's actually, there's two ways you can do this one as well, equals V over R, which equals, now in this case we have got the same voltage, haven't we? We've got the same voltage, and it's down here, 3.78. Okay, so 3.78 divided by, and this time the resistance is different because we're focused, I3 is on R, is the current going through R3, so 680 ohms. Okay, 680 ohms there, which equals, and we'll just whack that out again, 3.78, oh, we need the calculator this time, or at least I do, 680 equals, okay, that's in milliamps, shift engineering, oops, do that again, okay, which equals 0.00556. It'd be nice to have 3 5s, but unfortunately we have that 8, which rounds it up, amps, okay, which equals 5 point, hang on, sorry, we had another interruption there. Anyway, we were just doing milliamp conversion by the look of it. 5.56 milliamps. Let's actually just focus on this column here though, because there's a clever way you can do a bit of proof checking here. We can actually look at these and go, okay, let's add these two here. In fact, let's just go 0.0056 plus 0.00378 equals, what do you look at that? Well, it seems a little bit odd, but the answer is actually this here. These two, of course, which is these two currents, should add to I2 plus I3 should equal I1, and there's I1 there. Okay, so whether I did a little, oh yes, I left out of, in fact that was terrible, didn't have the detail there. It would have come out with a good answer had I plugged that in better. Okay, so we have solved everything. I should have said you could also subtract I2 from I1 to get I3. So you could have gone I3 equals I1 minus I2. Again, it's not an Ohm's law thing. It's what we call Kirchhoff's law, because this I1 comes into here, and then some of it goes that way, and the remainder goes that way. So that is also legit, and that would give you the same answer. But anyway, we've done the calculations now, and we can march on to some measurements.